So let's take a look at some important examples of acceleration where we can use this idea of finding delta v in order to learn the direction of the acceleration. So the first important case is movement with a constant velocity. So here's a motion diagram showing that. We can see the object is going equal distances in equal times. So we now need to pick one of those locations, one of those points the particle is at, to calculate the acceleration. Now we can't do either the first point or the last point because we don't know what happened before the first point or after the last point, but any of the four interior points would do. So let's pick that point right there. So if we pick that point right there, then the initial velocity will be the velocity just before the particle reaches there. In other words, that's the initial velocity. And then the final velocity for our calculation will be the velocity just after the particle is at that location. In other words, that's the final velocity. So now we have our initial and final velocities, and we now want to find delta v, the change. So there's our final. The initial points to the right, which means negative v initial is going to point to the left. And if we put those together head to tail, like that, we can see that the change is 0. If you take one vector and you subtract an identical vector, you're going to get 0. So if delta v is 0, that means the acceleration itself is 0. So the acceleration is 0 at all those interior points, and so that's the first important case. Whenever an object is moving with a constant velocity, the acceleration is 0. Now let's imagine what would happen if an object was speeding up without turning. So here's a motion diagram showing that. You can see the pictures of the particle get farther and farther apart. Again, we need to pick one of the interior points for purposes of finding our acceleration. Let's choose that one right there. So there would be our initial velocity, the velocity just before it reaches that point. There's our final velocity, the velocity just after it reaches that point. Now we need to find delta v. So there is v final, v initial is to the right, negative v initial will again be to the left. So if we place those head to tail like that, we can see that the difference is no longer 0. So if we find the difference by starting at the beginning of the first vector we drew and run in a straight line to the end of the second vector we drew, there's going to be our delta v. So you can see that delta v points to the right. And so if delta v points to the right, that means the particle is accelerating, and it's accelerating in that direction, to the right. In fact, that would be true at all four of the interior points in this motion diagram. So look carefully at the direction of the acceleration and the direction of the velocity. You can see that they are the same. In fact, anytime an object is speeding up without turning, the acceleration will always be in the same direction as the object's velocity. The next case we want to consider is an object that's slowing down without turning. So here's a motion diagram showing that. You can see the pictures of the particle get closer and closer together as it moves to the right. Let's pick that point right there for purposes of finding delta v. There's our v initial just before. There's v final, the velocity just after that point. So there's v final. Negative v initial is going to point to the left. We put those together head to tail. Again, they're different. The delta v is not 0. And again, if we start at the beginning of the first one, v final, and run in a straight line to the end of the second one, v initial, you can see that delta v now points to the left. Delta v is not 0. That means the particle is accelerating. And since delta v points to the left, that's the direction it's accelerating, to the left. And that would be true at all of the points in our motion diagram. So now look at the direction of the acceleration compared to the direction of the velocity. You can see that they are opposite. And that will always be true anytime an object is slowing down without turning. The acceleration will always point in exactly the opposite direction as the velocity. By giving the acceleration a direction, we can describe both speeding up and slowing down by looking at the direction of the acceleration compared to the velocity. If they're the same direction as each other, the object is speeding up. If they're opposite each other, then it's slowing down. The last case we're going to consider is what happens if something is turning but not changing speed. So here's a motion diagram that shows that. We're going to pick that point for purposes of finding delta V. There's V initial, there's V final. So to find delta V, we can draw V final. V initial is down and to the right, so negative V initial would be up and to the left. If we place that head to tail with V final, we get this picture. And if we go to find delta V, there's our delta V. We go from the beginning to the end of our chain of vectors. And you can see delta V points down and to the left. It points inward in the direction that the particle is turning. So if we put that in the diagram and we imagine what it would be like at the other three interior points, we can see that when an object is turning, the acceleration is going to point in the direction of the turn. This is an overhead view of the particle. It's turning to its right, and you can see the acceleration is to the right. In fact, if we went to the instantaneous values for the velocity and acceleration, we would see that the velocity and the acceleration are in fact exactly perpendicular to each other. They're not quite perpendicular in this diagram because these are just average values, but if we went to the instantaneous values, if something is turning but not changing speed, then the velocity and the acceleration will be exactly perpendicular to each other. So these are the most important cases we're going to consider. Of course, something can both turn and change speed, and in that case, the angle between the velocity and the acceleration will be something else. The angle between the two is 0 degrees if they're speeding up. If the object is slowing down, the angle between the velocity and the acceleration is 180 degrees. If the object is turning, the angle between the two is 90. If you're speeding up and turning or slowing down and turning, then the angle will be something else. Between 0 and 90 if you are speeding up as you turn, and between 90 and 180 if you are slowing down as you turn. So those cases are important too, but these 4 cases on this slide are the most important. These are the simplest ones where you're changing only one aspect of the velocity at a time or not changing the velocity at all.